Welcome to the NSX Advanced Load Balancer Operation Workshop video series. My name is Juan, and in this series, we will continue to talk about understanding the NSX ALB architecture. In this part of the video, we'll be talking about the service engine failure detection, the service engine group settings, the service engine as a router, scale out mechanisms, and BGP support. Before we get going, let's look at the HO topology. This is an environment that we have provisioned and we will use to follow all the examples as we go through the content. You can access this lab on your own at any given time. You feel free to pause the video, go to the link at the bottom of the page, and follow along, or just follow the guide at your convenience. Let's talk about SE failure and self-healing. Now, the service engine failure detection is essential to achieving high availability and ensure minimal disruption. We need to be quick and effective at determining when a service engine has failed. AVI can use three methods in order to detect service engine failure. The first one is the controller to SE detection method. The controller periodically sends heartbeats to the service engines to determine their state. We can also use the service engine to service engine detection method. This is communication within the service engines. Or we can use BGP router to SE failure detection. This is particular to BGP. Now let's talk about the controller to service engine detection method. The controller, again, periodically sends heartbeat messages to all the SEs in the group every 10 seconds by default. If there is no response for a specific SE for 6 consecutive heartbeat messages, the controller concludes that the SE is down and generates a service engine down event. So it's going to take around a minute for the controller to determine that a service engine is down. Once the SE has been declared down, now the controller moves all the virtual services that has previously placed on that service engine to a different service engine. Now remember that the controller takes care of the life cycle of the virtual services, your applications running on the service engines, so it can take that configuration and just place it on a different one. Let's talk about the service to service engine failure detection method. Now, the controller to service engine method is limited to the management interface. This method will not detect failures on the data interfaces of the SEs. Now, the service engine data path heartbeat mechanisms uses the data interfaces to exchange messages, heartbeat messages between the service engines. And there are two modes for this. We have the standard mode and the aggressive mode. Depending on the type of service engine deployed, one of the following SEs to SE inter-process communication is used. And we have the following ones. We have the custom ether type. This is the default mode applicable when the SEs are in the same subnet. In some environments, the ether type is not supported, so we have to use IP encapsulation. The SEs are assumed to be in the same subnet, and these can be enabled through a CLI. And we have the last one, the IP packets that are applicable when the SEs are in different subnets. So let's take a quick look. Let's just go to our environment and take a look at what are the difference between these two. So let's put my drawing skills to the test. Okay, so we are gonna select just a couple of boxes here, and they will represent service engines. And we're gonna have also a controller here, a bit bigger, and let's just put some labels on. So we have the controller, and we have service engine 1 and service engine 2. On a regular deployment, we have one subnet here for management. The controller is connected to it, and the service engines are connected as well. Therefore, all the heartbeats happen in this. Now, our controller to SE management heartbeats are only happening here. But what if we have some backend servers here? I apologize again for this drawing, but kind of paints the idea. So this is how the service engines will send traffic. So they get traffic. They deliver traffic to the pool members by using this data interface. Now this can fail as well. And then, I apologize, there's some interruption here with the RDP session. Now, let's the SEs can send heartbeats from within this network, and that's the SE to SE. So let's take a look at some of the configurations of those settings. Now, in the case of the BGP to router, when we have BGP in the environment, we use bidirectional forwarding detection for the SE failures. On detecting the failure, the BFD informs the router not to use the route that has failed, the route that the SE has advertised and is removed from ECMP. BFD provides sub-second failure detection, much faster than BGP timer. So it's the best and faster failure detection method. Now let's take a walk through what happens, what actions happens when there's a SE failure. Consider an SE group which a virtual service has been scaled up. Now that means that it's running on at least two SEs. The primary SE sends periodic heartbeat messages to the secondary SE. How frequent those messages are delivered, it's based on the settings. If you're using aggressive and standard, we're going to take a look in just a moment about what those values are. And then a string of consecutive response failures to the heartbeats from a particular SE indicate that the given SE could be down. Now, when the primary suspect that the SE is down, it's going to inform the controller, and the controller is going to initiate some echo messages to the suspect SE. Now, those echo messages, consecutive response failures, indicate to the controller that the service engine is down. Now, the controller declares the SE down through the SE down event, and then the actions to move the virtual services out of that service engine proceed. Now, let's take a quick comparison here between the standard and aggressive. So, when we're working with standard values, we need 10 consecutive failures every 100 milliseconds between the SEs. After that, we have 4 consecutive echo messages every 2 seconds. So we have 1 second for this to complete, and then 8 seconds here for a total of 9 seconds that we take to declare that the service engine is down. Now, switching to the aggressive mode, we have 5 consecutive every 100 milliseconds. So we have 0.5 seconds here, and then 2 consecutive messages fail every 500 milliseconds from the controller to the SEs. That's 0.5 plus 1 second for a total of 1.5 seconds to determine. Much aggressive again. These values, again, these methods can be enabled, the aggressive method can be enabled through the CLI. However, we recommend the standard way. Why? The aggressive is, there's a use case for very specific environments. The aggressive can lead to false positives depending on the network topology. That's why that feature is only enabled through the CLI. You're going to see through the configuration of the platform that some of these advanced features that can potentially have an impact on your traffic are reserved for the CLI, meaning that in order to enable them, you need to be an advanced user or take some consideration, something that cannot quickly be overlooked and maybe enabled on the UI. That's the reason why this is only on the CLI. Let's talk about self-healing. The SE failure is handled and determined by the HA mode. As we have explained, every service engine group has its HA configuration, and every service engine group behaves as a self-healing fabric, responsible for the continued operations of the virtual services that have been placed on them. You can have different service engine groups, and every service engine group will take care of recovering the SC and achieving the HA that has been configured through the UI or the CLI or the API. Now, when we have a headless operation of the SCs, we can continue to work even if the control plane is non-operational. As we discussed previously on the other videos, what we lose by being on a headless mode is the ability to create new virtual services or make changes. But even when the control plane is not available, the applications will continue to run. Here we have a comparison of the different how the failure is handled. First of all, we have an N+M failure, right? We have several applications that are running on two active service engines. In this case, we have a buffer of 1 equals 1, and that service engine is just a spare one. It's running. So we have all the applications running distributed on these active ones. Now, if one of them fails, it will impact whatever applications were running on this service engine. And at the same time, the controller will place all those virtual services on the buffer SC. So it becomes an active service engine. Now, there's an impact, but it's an impact on a fraction of the applications placed on that service engine group. Now, at the end, the operations restored and full performance is restored. And again, after that, the controller can take action and replace that. If we're dealing with a vCenter type cloud, for instance, where we have control or the controller can take care of the life cycle of the service engines, the controller will spin up a new service engine for you. Now, you might think, what happens when that service engine that has been determined to fail comes back for any reason? Maybe somebody shut down the VM and now the VM is available. The controller will not try to move those virtual services from the new SC or the newly active SC back to the original SC. That SC is going to continue to run there. And depending on your configuration, if nothing happens, there are no more changes in your environment, that SC will become idle. And the controller has a timeout value per service engine group. And then if the SC is being idle for that amount of time, then the controller will delete it. So we don't want to waste resources and leave things running indefinitely. So that service engine will be eventually removed. Let's compare it with an active-active service engine group configuration. In this configuration, we have active-active service engines. The virtual services have been placed on them. Now, if we lose one of them, because every single virtual service is running in at least 2 service engines, it doesn't impact anything. Now, the applications will continue with reduced performance if the virtual service, your application performance, cannot be delivered by a single SC. But traffic will continue to flow. Then, when the service engine comes back or the controller can create and replace that service engine with a new one, then full performance is restored for all those applications. And the last one is the legacy active standby. Now, in this scenario, we have this active one and a passive and a completely standby one. If that goes down, then everything moves. And that failover will be noticeable to the applications. But then because we have one service engine pre-provisioned ready on standby, then it will take over in a short period of time. Let's take a look at a few different service engine group settings. This is, again, part of the infrastructure configuration. We have networks and routing. Let's see what those mean. The networks tab represent the list of discovered and manually configured networks within the cloud. Individual networks can be configured for DHCP or for static IP address allocation. And those network settings can be edited by clicking on the pencil. So here's an example of that network section. You have 3 networks here on that VMware cloud. The name of the network, we have the discovered subnets. They can be auto-discovered depending on the virtualization orchestrator. In this case, it's VMware, so we have discovered a few networks. And we have the configured networks, and those are the ones that we manually enter. So let's take a quick look before we jump into the route section and take a look in the UI. Yeah, so we're gonna launch the browser, go to region A. It doesn't really matter where you go if you're following, and log into the controller. And credentials for all this. If this is the first time that you see the HOL, all that information is provided in the HOL. Let's switch to the infrastructure on the left-hand side. And we have, let's just frame this for a second. We only have one type of cloud. One single cloud is the default cloud, and it's a type of vCenter. Now, let's go to the service engine group, configuration, back to the networks. And because it's a vCenter cloud, we have discovered all these networks, right? And then we could manually create ones. We can just take a open with the pencil and take a look at what this is the range of that subnet. We can take one of that and generate a static IP address pool. And that there are 2 different ways, as we just saw in the presentation. We have DHCP or we have a static pool. Now we can use those subnets for allocating IPs for the data NICs of the service engines. And those data NICs are the ones that will be used to communicate the SC with the backend servers. And we can also take those static ranges and take the VIPs, allocate the virtual IPs that for those service engines, for those virtual services, and place them on those subnets. So there are multiple uses for these networks. Let's switch to the presentation. And let's discuss the other section of the infrastructure tab, and is the static route. So static routes may be used to configure the next hop path for routed traffic to the backend servers. A static route can be set as a default gateway as well. And we can access those on the infrastructure section, routing, static route tab. Now, this is how it looks like. So again, all these settings have a scope. So we have to select a cloud for that configuration. So right now it's VMware Cloud, and we're telling the SC how to reach these subnets. So in this case, 10.144.66.0/24 will be accessed through this IP. If we were to look on the UI, how does it look? Then again, is the routing tab, and there's only one default cloud here. We only have one cloud configured. Then we can click on here, create. This is the subnet CIDR and the next hop. And in some cases, we need to configure that depending on your environment, depending where the backend servers are. This is how you can alter that behavior. Let's switch to the presentation. And again, this is an example of how we do that. There's a prefix, the CIDR, and where is the next hop. Here it is. Now, let's talk about this use case, the SC as a router. We can configure the SC as a router. So the backend servers will receive the traffic and will send it back to the service engine because it has been configured as their default gateway. Now, there's a use case for this, and it's called preserved client IP. Now, this preserved client IP is enabled under the application profile. Now, if you want to use a preserved client IP, you have to think that IP information in the sender is going to be received directly by the backend servers. Now, in order for them to reach back to the client, they have to send it to the SC. So in this case, we have to configure the service engine as the default gateway for those servers. We'll have to modify the backend server network configuration. And then when it goes back to the service engine will act as a router and will know how to reach the client and deliver the communication back to it. The IP routing on SC is supported only with no access clouds, no access VMware, LSC, Linux Server Cloud, and CSP, Cisco CSP. Works with legacy active standby only. And there's a reason for that. We'll see in the diagram in just a moment. It can be enabled only on the global VRF, and the backend servers must be on the same subnet. So several conditions to be able to work with this. Again, if preserved client IP, and this is typical to when we're dealing with layer 4 traffic, right? If we're dealing with HTTP, for instance, there are other ways in which you can use to communicate to the backend servers where the traffic is being originated by using headers and different properties of the protocol. Now, for L4, we have this option, and there's another one that is not mentioned here that can be used to also preserve client IP, and is DSR, Direct Server Return. So let's take a look in the specific case for the SC as a router example. So here we have two service engines, and then again, it's legacy HA active standby, and we have a floating IP. So we have a floating IP in the front end and in the back end. This is the floating IP in the front end is the one that is going to be advertised for reaching those backend servers. And we need a floating IP also in the backend. So when we configure the backend servers, they need to talk back as a default gateway to the floating IP on the SCs. Again, those floating IPs, if one service engine fails, then those floating IPs will move to when the standby becomes the active. And that's one of the reasons why we cannot configure the legacy or this preserved client IP, this ESC as a router on different types of HA. For instance, if we have N+M, then we cannot guarantee which one that the traffic will have asymmetric routing traffic in this case, and that will create complications. Again, if your service engine group HA is N+M or active, and you need preserved client IP for L4 traffic, there are other methods, like I mentioned before, the direct server return. Now, in order to make this work, we have to create it on the CLI. So we have to define what is called a network service, and that network service will have that information for the communication. So we're enabling routing. We're doing a floating IP. This is the definition of the floating IPs on the backend and the front end. And on the front end router, we have to configure static routes to the backend service networks, pointing to the front end floating IP as the next hub. And again, on the backend service, we need to configure the backend floating IP on the SC as the default gateway. Different things have to happen across the environment in order to make this work. Let's switch gears now and talk about the scale-out mechanisms, L2 versus L3. Now, so far, when we have talked about HA active, we've been talking about LA2 scale-out. In LA2 scale-out, we have a combination of virtual IP and port, and that is placed on the primary C. That VIP can only be advertised in one of the primary Cs. So what happens? The primary C creates L4 tunnels to the secondary service engines, and as it gets the traffic, it will determine if it will be itself processing the traffic or is going to offload it to a secondary SC. Now L2 forwarding from primary to secondary SCs. This is what the picture is showing. Now the primary SC behaves as a load balancer of load balancers. That is pretty much what it is. And now before going to the L3 option, remember that when we configure, and this is the point that we touched on a previous video, we look at the service engine group configuration. When we were configuring the default group, we talk about these advanced settings. On advanced, we have the scale per virtual service, and we have a minimum for it. For active will be 2, but the maximum is 4, and is the maximum in any situation. We should not be going higher than 4, and there's a reason for that. When we're dealing with L2 scale out, because this primary service engine can become a bottleneck. We've done different performance studies and analyses, and it's not optimal when you go further than 4. So if you go with more than 4, then there's a performance degradation. Again, there's a bottleneck in that primary SC. So what options do we have? L3. So let's talk about L3 now. In L3, we have these clients that are reaching these service engines, are providing the services, the load balancing services for this web server pool. Now, each SC advertises a route to the VIP, the virtual IP, to the BGP peer. So the clients are looking for VIP1 and a port. Then they send traffic here, and they eventually get to the router. Now the router has received the same route, multiple routes for the same VIP. Every single SC is advertising that VIP. And then the BGP router uses ECMP to distribute the traffic. So you're going to have a few routes, and then ECMP will, by virtue of ECMP, you're going to have multiple ways to access that. And then that's going to redistribute the traffic across those. And eventually the service engines will reach to the web, the backend servers, in this case, this example, web server pool. Now, let's talk about the BGP support for Elastic HA. We support BGP for legacy active standby, the traditional method, and we also support it for active and N+M. Comparing these two solutions, L2 versus L3, the primary in L2, the primary AC for a VS is tasked with the distributions of the VSs among other ACs. So for instance, if you have SSL termination in configure for one virtual service, that primary AC will receive the traffic, and it might choose to do the termination there, or depending on how busy it is going to forward that. So some of the processing power can happen on different SCs. It's going to offload that to a different SC. With L3 scale out, we use route health injection, RHI, and equal cost multipathing, ECMP, to distribute the VS traffic among the SCs. With L3 scale out, the VSs can place in up to 64 service engines within a SE group, and the route will be advertised in multiple service engines, and that every single service engine will send its IP as the next hop. Now, the BGP router sees multiple hops, and then it uses ECMP to load, share the traffic. The L3, again, is supported only with VMware and Linux Server Cloud, OpenShift, and Kubernetes ecosystems. The other integrations, public cloud, especially the networking configuration, is different, and therefore it's only supported for these environments. We have a plus here that when you use L3, BGP, bidirectional forwarding detection is used, and it's a very optimal way to detect SC failures. Then when you have applications that require a lot of traffic, very intensive applications, then BGP it's always the best way to scale out. How we configure BGP? Then you have to go to infrastructure, routing, and select the BGP peering tab. Remember that the scope of this BGP applies to a cloud. So when you enable BGP for a cloud, then it will be also available for the service engine groups on that cloud. Now, when we go into BGP, then we have to set things like the autonomous system that we'll be talking to, and some MD5 secrets, and the different regular parameters that we'll use to create a peering between the service engine and the router. And select, in this case, we're going to be using BFD, and we're advertising the VIP and the SNAT. Then, before going there, let's switch to the RDP session, and let's take a look and see how it looks like. Remember, when we have in the infrastructure tab, we go to routing. Here we are familiar now with the static route. Then we're going to go to BGP peering. BGP peering currently is disabled for this type of lab. It's a simple environment. And this is where you would configure the BGP settings. You're going to use a BGP, and then the different parameters. This is how you enable your cloud for BGP. Now, there's only one last thing after doing that, and that's if we go back to the presentation. When we're creating the virtual service and we want to use that BGP feature, then we have to select advertise BIP via BGP. And that's an advanced parameter, and it's configured here. That is essentially what is left for us to configure. And that concludes this video. I hope the information was valuable. And if you want to have a play for yourself, check out the hands-on lab and give it a try. Thank you.